Hi everyone. In this lecture, what we will do is we'll solve some problems on Fourier transforms. First things first, what is a Fourier transform? Fourier transform is along the side of Laplace transform itself. It's also one of the integral transform for any functions. So, which means some of the problems that we are unable to solve it in the own domain, we usually transfer it to some other domain and we'll solve it very easily over there, and then we'll transfer back to the original domain and solve it. Okay, so that's how the any transform works. So especially integral transforms like Laplace transformation works very well in that result. Now, same in the same process, Fourier transform is also going to work in the same process. So what is the definition of a Fourier transformation? So given any function f, let me write it here. So given any f, we define Fourier transform of f of x. Okay, f of x is actually equal to 1 divided by square root of 2 pi into integral minus infinity to infinity f of x into e to the power isx into dx. Okay, fine. So we call this particular transformation, or we call this as Fourier transform of f. Okay, that's all. We denote this by capital F of s as usual. What we do, denote it using in the Laplace transformation, we denote it similar way as capital F of s itself. And similarly here also we can denote it as capital F of s. So nothing harmful. Okay. So if you know this, then this implies we can also define a small f of x itself. If you are given capital F of s, is simply 1 divided by square root of 2 pi into integral minus infinity to infinity, where capital F of s is given to you. So f of s into e to the power minus sx, isx into dx. Remember, note this here, plus ixx, and then here minus isx. Okay, fine. So we usually denote this as pairs, or in other words, Fourier transformation first. I'm sorry for this very loud voice that is generated by my son actually. Okay, so that's the Fourier transform pairs, or in other words, Fourier transform of f of x and its inverse transform of it. Okay, fine. Now, first things first, we can probably solve one problem and then we'll look at the properties of the Fourier transformations as we do it in any of the transformation techniques. All right. So let's solve this problem. Find the Fourier transform of f of x equal to e to the power minus x squared divided by 2. Okay, that's a question. Now, how do you solve this problem? Remember, it's just an integration to be done. That's all. So nothing too fancy here. The problems are very simple as long as you know integration. That's all. So what is the Fourier transformation of the given function? F of x is actually equal to 1 divided by square root of 2 pi into integral minus infinity to infinity f of x into e to the power isx by definition. Correct? No, that's the definition exactly, and I'm writing here. Now, what is this? So further, this is 1 divided by square root of 2 pi into integral minus infinity to infinity, and f of x has been given as e to the power minus x squared divided by 2, and here e to the power isx, right? So isx into dx. That's all. Now what we can do is we can write it as 1 divided by square root of 2 pi into integral minus infinity to infinity e to the power minus x squared divided by 2 plus isx into dx. So that's it. Okay. What else we can do? Now further, what we can do is probably we can take this 1 by 2 outside. So 1 divided by square root of 2 pi into integral minus infinity to infinity e to the power, this is minus half can be taken outside. Therefore, that will give you x square plus, remember, I have taken minus half, which means I have actually, that means is multiply and divide by 2. Therefore, I have taken minus half, and hence it's going to be another minus I'm sorry, 2isx, right? 2isx, because 1, 2 has been taken out from the denominator and the other 2 is retains. Okay, good. So how do you solve such problems? We usually write it in a fashion that where we can express the function in terms of some function of ax plus b. That's how we do it, and then we try to take the constant outside, and then we want to evaluate it. That we will achieve by using the method of completion of squares. So what we do here is, we write this as 1 divided by square root of 2 pi into integral minus infinity to infinity e to the power minus half times, what is this now? Let's do it in the right hand side here. You see that x square minus 2isx. So this is the term that we have, which means this is the term that we have. It is minus a square minus 2ab. Now we want to complete it by b square, so that it will become a minus b whole square, and we also have to subtract it by b square, so that this term will not be affected. This term will not get affected. So what is the b we have to choose? Now, as you notice here, this is simply 2 is already there, and a is simply 1 here, right? So 2 into 1 into, and remaining is the b. The b is here is, that's all, correct? So isx actually. Am I right? No, not isx. Just a is here. Actually, a is 1 into x. So, sorry for that. A square, right? So that will become 2 into a is x, so x into, and remaining terms is I into s. So this is my b. So therefore, if I add b square, that means I should add is square. I also have to subtract is square. So therefore, this term will become x square minus 2isx plus is whole square minus is whole square, which is I square is minus 1, therefore it's plus s square. Okay, that means this will become x minus is whole square plus s square. Great. And therefore we can substitute it here. That is x minus is whole square plus s square. So hopefully you don't have any problem with this. So this is simply replaced from this place. Okay, this one was giving together into dx. Of course, I forgot it here. I'll add it here. Okay. So now, of course, s is a constant term over here. That means e to the power x square is also constant. So I can bring it outside. 1 divided by square root of 2 pi e to the power minus half s square by 2, which is minus half into s square, which is e to the power minus s square by 2 into integral minus infinity to infinity e to the power minus half times x minus is whole square into dx. Okay, good. Now all that we have done is we have just simplified this expression into e to the power ax plus b whole square format. Okay, fine. Now this is helpful because what we can do right now here is we can substitute it by something and then get the answer. That's the idea. Okay, what's the substitution we'll make? Probably we can also think of this as this divided by square root of 2 and hence whole square. Therefore we can take this off. Okay, and therefore this one will give you just minus something. Therefore what we can do is we can write now, let u is equal to x minus is divided by square root of 2, and then this implies what is my du, meaning du by dx. Actually du by dx is actually equal to 1 by root 2 into 1, and that further implies du would be equal to 1 by root 2 times dx. So when you substitute u equal to this, and you get the d. Remember, the limits are also from x equal to minus infinity to x equal to infinity. So you also have to change the limits to u. So as x equal to minus infinity, then by the substitution, you also have u is also equal to minus infinity, right? And similarly, as x equal to plus infinity, you also have u is equal to plus infinity, because infinity minus is divided by all of them are constant, so it's going to retain infinity. If it is minus infinity, it's going to retain minus infinity. That's the idea. So the limits are also changed. Therefore, we'll write this as f of x, and hence we can continue from here. So this implies the f of x is actually equal to 1 divided by square root of pi. By all the substitution, we'll have e to the power minus a square by 2 into integral. Now this time e to the u equal to minus infinity to plus infinity into integral minus, remember this was substitution that we had, so u into du was 1 by 2 times I'm sorry, I think yeah, which means du is 1 by 2 times dx, which means what do I want was dx. So dx is actually 2 times du. So we write that here. So 2 times du. Okay, fine. So this further implies that 1 divided by square root of 2 pi into e to the power minus a square by 2 into this is simply 2, so 2 has been taken outside, and e to the power minus u, which is integrated by like this. So e to the power minus u divided by the coefficient of u, which is minus 1. Okay, fine. And the limit is minus infinity to plus infinity. Now what is the answer? So the upper limit substitution, which will give you e to the power minus of minus infinity, will be e to the power infinity. Correct? Yeah. Oh, sorry. I think I made a small mistake. Here it was u square, right? So it should be u square. Here also it should be u square. Of course, then the integration is wrong. So we got e to the power minus u square into 2u. Oh, that means we also have a small mistake in the other one as well. Oh, it's root 2. So square root of 2. Sorry, guys. So e to the power minus u square into square root of 2 into du. That's it. Okay. Yeah. So then now what is the answer? Now you know answer for this, right? Because this has been already discussed in your school or something. So what is e to the power minus u square into du? Which is simply, the answer is root pi. So that's why this effort. So therefore this one is 1 divided by square root of 12 pi. Of course I can right away cancel it here, right? Because this is 2 and then this root 2 gets cancelled. And therefore this one will give you 1 divided by square root of pi e to the power minus a square by 2 into this e to the power minus u square, which is integration is actually equal to root 2 pi. Therefore this and this gets cancelled finally, and the answer is minus e to the power minus a square divided by 2. Okay, yeah, that's all. So that is the Fourier transform of f of x, where f of x equal to e to the power, I think, minus x square by 2. Correct? Yeah, e to the power minus x square by 2. So actually what has happened here is this little thing has happened, that Fourier transform, whatever we try to apply, we have obtained the similar Fourier transform. In fact, actually we obtained the same Fourier transformation. So you see that only the variable has not changed. It has not changed any of the function's behavior. Such kind of Fourier transforms are actually called as self-reciprocals under Fourier transformation. Okay. Of course, this is not the case for every function. If this is the case, then there is no need to actually study Fourier transformation. So some functions are actually having self-reciprocal under Fourier transformation, which means whatever the function you have given, and the same function would have been got it as an output or got it as a Fourier transformation. Okay, fine. So this one is specially called as self-reciprocal Fourier transform, or self-reciprocal under Fourier transform. That's the better way to say Fourier transform. Okay, fine. So let's revise what we have done here, and then we will wind up the lecture, and we'll see the rest of them in the next lecture. You see, the Fourier transform of any given function has been written as, or defined as, 1 divided by square root of 2 pi into integral minus infinity to plus infinity f of x into e to the power isx. Now we want to solve the problem of saying find the Fourier transform of given function e to the power minus x square by 2. Now all that we had here is we just utilize this definition. That's all. So f of x was 1 divided by square root of 2 pi into integral minus infinity infinity f of x into e to the power minus isi e to the power isx into dx. Now substituted e to the power minus x squared by 2 for f of x, because that's what the function has been given. And then we just did some small manipulations so that we can perform this integration a little better. In fact, if you already know that what's happening over here, you can write this particular, you don't need to actually complete this substitutions here. So you can directly do it here itself, but it's okay. So we'll do it slowly in the future problems. But at this stage, the substitution method was helping us to bring it down to minus infinity plus infinity e to the power minus u square into du, which was which was square root of pi. There's a proof available. You can check it from your previous classes. And therefore, a Fourier transformation of given function was simply e to the power minus s square by 2. Okay, fine. So since the Fourier transform and the f itself has been same, there's nothing has changed except the variable. We call this particular function as a self-reciprocal, or this function is a self-reciprocal function under Fourier transformation. Okay, fine. So that's all. That's the end of this particular first lecture, and I'll see you in the next lecture with more problems. Thank you guys.